In example 8, we want to find the volume of a pyramid whose base is a square with side L and whose height is h. Now, if we place the origin 0 at the vertex of the pyramid and the x-axis along its central axis, as in this figure, now any plane P subscript x that passes through x and is perpendicular to the x-axis intersects the pyramid in a square with side of length s, and we can express s in terms of x by observing from the similar triangles in figure 15. So here we have one small triangle, which would be where that cross section is, and then we have a larger triangle. So what that means is that we can say that as the distance here, or the height of that triangle, is x, would correspond to the height of the larger triangle. So therefore we go from x to h. Now we know that if we're looking for this piece, it's going to be s divided by 2, which is the same thing as L divided by 2. So S divided by 2 corresponds to L divided by 2, which then equals S over L. And so S is going to equal Lx divided by H. So now another method is to observe that the line OP has a slope of L divided by 2H. And so its equation is y is equal to Lx divided by 2h. Thus the cross-sectional area is the following: a of x, which is equal to s squared, which is equal to L squared over h squared x squared. And the pyramid lies between x equals 0 and x equals h. So the following would be the volume. So going from 0 to h, we have L squared over h squared x squared dx. Taking the antiderivative, L squared and h squared are constants. X cubed over 3, evaluating it from 0 to h, gives us a volume of L squared times h over 3. Now, we didn't need to place the vertex of the pyramid at the origin in example 8. We did so merely to make the equation simple. If instead we had placed the center of the base at the origin and the vertex on the positive y-axis, as in figure 16, you can verify that we would have obtained the integral in the same way.